Hello, this is the 8th time recording. Hello, this is the video explanation for the MEEN 305 Project 1 design of a beam code analysis. This video is to explain behind the code that we used and how it is used to computate the factor of safety, mainly for the factor of safety of the beam. So first, let's get started with a rectangular cross-section to show you the example of how the code works. The code is provided to us from the class, and we were in charge of changing the variables in order to fit our need. So let's get started. So for a rectangular cross-section, assuming a constant rectangular cross-section, so it does not taper throughout any of the length, um, we have a column over here regarding the two dimensions that are needed to list the cross-section. So we have the height and the base. In this section for the cross-section, we're also given the moment of inertia and section modulus. The calculation for the section modulus is done with the moment of inertia over height. And then, so for each variable, or for each different cross-section, the also have light jazz music in the background, good vibes and stuff. So for each different cross-section, we have to change the moment of inertia equation to match the cross-sectional needs. So for example, we have the circular cross-section right here. It has a different moment of inertia compared to the rectangular cross-section. And same thing for, I believe, section modulus. Never mind, I take it back. Section modulus is exactly the same. But for the most part, the moment of inertia is changed, and then everything else is provided to us via equation. And let's first explain this. So for the initializing variables to specify the dimensions of the cross-section, it is different depending on what cross-section we have. So for example, this is a hollow square tube. So for the hollow square tube, that was my ringtone, I'm sorry about that. For the hollow square tube, we have an outer base length and an inner base length. And then for a circular cross-section, a constant circular cross, so a filled circular cross-section. There's only one diameter. But our design that we ended up choosing is a hollow tube, which is not on this Excel. I'll pull up that Excel in a bit. But first, let's explain. Actually, I'm just going to pull it up right now. All right. I'll just go pull it up right now. There we go. So in this Excel folder, this is named video demo for the calculations. Our final design was a circular tapered tube, which means that the design of the tube, the length, or more, I would say the radius of the tube, increases to a certain point, and then it decreases again. As you can see here, it starts out with initial diameter, and then it goes to increases linearly to a certain diameter, and then decreases again back to the original diameter. So in this Excel file, we have the PLA material. This is used in different calculations. I believe it's do we use it at all? When do we use this? Okay, so it is used, I guess, but all of these variables are up here to either calibrate or specify where the load is given. For example, we have this section where we have P for load, and then load position, and then the length of the whole beam. In actual process, our beam is 9 inches wide, but for the sake of this Excel file, we are only looking at a certain portion from the supports. So the length is from one support to the other. And I will clarify why this folder is slightly different from the other ones is because we ended up choosing a cross section that, well, I guess I'm explaining it now. We are choosing a cross section that somebody just needs. We are choosing a cross section that doesn't change if you rotate it in any way. So circular cross section, you rotate that 90 degrees, doesn't change. So, but for other cross sections, you can see on the bottom we have 0 degree and 90 degree rotated. For example, for the, okay, somebody just texted me, hold on. All right, that was my group relating to this video. So for example, we have the I-beam design. And since the I-beam design, why is there, okay, well, ignore that. Oh, what's this? I don't know what that. All right, this doesn't matter. Ignore the hashtag value exclamation marks everywhere. But the fact is that we have a design that is not uniform or not the same. The cross section, when it's rotated, will support a different um, load compared to, will support the load differently compared to if it was its original orientation. So that's why we had the design of 0 degrees and 90 degrees. But since we're on the circular cross section, it does not matter which way you rotate it, it will remain constant. Up here, finally explain the three. We have the initial conditions, two loading conditions. We have 5 pounds at midspan, which is 4 inches from support A. In this example, we have the uh, the second loading condition, depending on your team number, which is for, we have 13 pounds at 4.2 inches from support A. And since the loading is at a point not symmetrical with the center from, not symmetrical with the two ends of the support, we had to change the moment equation. As you can see, it's the only one that has a different format because it was copy and pasted from somewhere else. I think Google Sheets, because we worked on the Google Sheets and then translated it to Excel for the graphs. So now explaining the uh, dimensions. These two lanes are for the dimensions, inner and outer dimension, moment of inertia, given by this equation. Then the section modulus, which is mainly used to calculate von Mises stress. Then we have the shear force. The shear force is formulated in the uh, essentially in a similar format to Macaulay brackets, but in Excel. So you can see we first had to calculate the force at support A. And then from there, we added in the two other conditions that are triggered once they reach a certain point. Excuse me. So that's for the shear force. For the moment force, like I said earlier, oh yeah, down here, there's the density, volume, and weight calculation. This will change based off if you change these. I guess I'll just, I mean, in general, I'll just, let's see, 0.35. You can see the units shifting, and you can maybe see the graph shifting as well. This ended up being our final design, just because of the limitations of printing. But back to the code. So the moment of the moment equation is also formatted from the Macaulay brackets, which this term over here only triggers once this is positive. And for the most case, it will be negative because it is before when x reaches 4.2. So once x, the position, passes this point, it will trigger, and that's what leads to the decrease of the term. So we have the term increasing, and then we didn't have it decreasing. Similar to the equation for the tapered, radius diameter. Since we had to create some tapering increase to a flat line to decrease, what we ended up doing is we had a linear increase slope of 0.45 divided by 4. The 4 came from the halfway point of the beam, and then 0.45 just comes from a random variable we chose, and then we changed that various times to see if it will be better for our beam. But then say it increases until we reach the point, and I've decided that this is the region where it would flatline because the two conditions of our load supporting is at 4 and at 4.2 inches. So this is a range where it can evenly support the load in real life if we put the load at that point. So yeah, and then we put this constant, but in order to keep this continuity, the equations, oh my god, if Excel would, the equations we had to formulate it as the initial plus once it theoretically reaches 4.0. So if the slope continuously reached 4.0, and then minus its current position. So, because initially, if we just kept the same formula as this, it would based off of the previous position, which is 4.5. So the decrease would be based off of like 4.5 and not the, the actual slope itself once it reaches 4. That makes any sense. All right. So you can see the moment is adjusted because the side load here is different from the center load. And then you can see we have the factor of safeties here for stress analysis. While MESA stress is just an indicator of stuff, but we mainly care about these two, factor of safety and target factor of safety. For this project, we had a target factor of safety of 1.5. As you can see, we did not even reach close to 1.5, but that is only due to printing limitations where we had to have a minimum thickness of at least 0.13 inches in order for the printer to print our cross section. So that's why our factor of safety ended up being so high. These equations over here are for deformation analysis. We have the taking, um, the, I don't know how to call it, but this equation, it is to measure the rate at which the rate of deformation happens. So double rate. So we have, yeah, just a moment, and then we take the integral of that to get this, which is the rate at which the positions shift or the deformation happens. And then we have another integral. And then for these two are taken into consideration the constants that are created from integration. So you can see up here we have corrected constant, which is a result of some form of calculation. And we, as a result, the boundary conditions. The boundary conditions are, we're assuming a fixed, um, a fixed beam at which the initial deformation at x equals 0 is 0, and then the deformation at which x equals L, which is the length of the beam, is also equal to 0. And then it's where we plug in L into this equation so that we can get C1. And for this lab, C2 is 0 because we always satisfy this condition right here. So yeah, this is with in consideration the constants, and then now we can look at the graph. For this lab, we mainly cared about the factor of safety graph, and yeah, these graphs are more for analysis, showing you where how the beam is deforming with position, and then the rate at which it is deforming. So yeah, that is the explanation for the code for this project. And yeah, that should be it. Goodbye.